the previous class, we were looking at the multiple access. So we try to define the multiple access, that a common resource, we are trying to share that with multiple users, right? The communication resource needs to be shared by a large number of users. That's what we are going to call as multiple access, and we looked at a very good example of how a satellite communication achieves this, right? And we started with the types of multiple access. Initially we saw a technique called frequency division multiple access, called FDMA, right? For continuous time duration, the frequencies will be divided into sub-bands as shown here, right? And each of the frequency band gets allocated to several users, right? User 1 might get band 1, 2, second user might get band 2, third user might get band 3, and so on, right? Now, since you are allocating the frequencies to users, in order to separate the users on the receiver side, you need to design the filters, and because of the restrictions of filters, right, though ideally you expect a sharp cutoff, and it is not possible to get a sharp cutoff, and it's practically you have to go beyond your cutoff. Slightly it will go outside, so you need a guard band. Okay, that's the first use of guard band. And also these guard bands help us in avoiding the interference of neighboring channels, right? Two uses of them. And since it is a frequency domain, right, usage, so every semiconductor device we use in our communication to build the communication transformers, receivers, transceivers, whatever, right, they are non-linear in nature. So because of this non-linearity, right, of this, so you try to operate every resource slightly lesser than the actual capacity of the device. This is just to restrict the power usage, right, or right, other non-linearities, just to try to avoid other non-linearities in the system, right? So you see there is a term that is called as power back off whenever it comes to the FDMA techniques, and we will call this as a drawback. Okay, this is a drawback of the FDMA system. Okay, right. Then moving ahead. Now we consider a second technique that is called as a time division multiple access, right? So instead of dividing the frequencies into several bands, you divide the time into several time slots, right? So each time is allocated to a user. Normally this is a very small time what you call slot in terms of milliseconds, maybe microseconds or of that order, right? But each user gets a time slot. Again, it will be normally in a cyclic fashion, right? User 1, user 2, once again user 1, user 2, user 1, user 2, as it is. So if a new user comes, then a new slot will be created for the new user in the middle. Okay, like that. Again, we have some synchronization issues related to the communication device, because worldwide users will use this technique. Indicates every user might have their own timing issues, because their hardware may be different, or they may be located in a complete different region, etc. Because of all this, there will be what is called as a timing issue, specifically the synchronization issue, right? Just to overcome that, what we can do now is that we will use the guard bands in between the time slots, and that again will be a small time interval, right? In this particular diagram, we can see that we have used a guard band of 0.5, right? 0 to 2.5, 3 to 5.5, and 6 to 8.5. They are the actual time slots. But between 2.5 to 3, we have a guard band. 5.5 to 6, you have another guard band that actually separates, right, the time slot 1 and 2 or 2 and 3 respectively, right? So just to overcome the timing issues related to any circuit that is using the TDMA system. Then we have the advantage over here, as you don't have to worry about what frequency I am sending. There is no frequency restriction, because at a given point of time only one user is going to be there, right? So because of that reason, now what happens is that you don't have to worry about the non-linearity of one system affecting the non-linearity of the other system, no interference, etc. So you can make use of your device to the full extent of power, right? You can maximize the power delivery, or you can give full current, full voltage to that device. So you see that advantage of this particular technique is that you can operate the given resource, right, at its full spectral efficiency. Highest power can be allocated to each and every frequency of, right, that using which you can communicate. Complete band or complete bandwidth can be used, right, efficiently over here. Okay, so this is what we have seen so far. Okay, now we'll move on to the next technique, and this technique is called as the CDMA, or the code division multiple access. Right, so FDMA, right, you are going to share your resource by dividing the resource along the frequency coordinate system, like disjoint frequency bands. First point to remember. And later on we check the TDMA system, where your resource is shared by dividing it along the time coordinate axis. Correct? Disjoint time slots are the basic features of TDMA system. Okay, now both these two techniques constitute a most popular choice of the multiple access application, because you want to bring in what is called as a security aspect. Correct. So for example, let us consider scenario of TDMA, right? What time slot, who is going to send is predefined. There are three users. You know that, okay, the users are going to use the channel at the specific time. In the sense, if somebody knows who is going to send at what point of time, somebody can definitely access, right? Access that. That's the first thing, right? So far we never discussed about the security aspect of any of the multiple access techniques we consider so far, but now we bring that as well into the picture, because that's also very important. Correct? So let's check the frequency division multiple access once. In FDMA, each user gets a specific frequency. All the time he is using the same frequency, right? So you know that means you can try to maybe, right, interfere, right? Maybe you try to listen to that particular communication, or if you want to jam, definitely you can do the jamming of that, right? So communication might not be possible, or you may correct, you may put noise at that frequency. Many things can be done, right? So now the security is also equally important. So both the techniques we try to use to create something called as a hybrid. Okay, so this particular technique, which is called as a code division multiple access, right, uses a hybrid combination of TDMA and FDMA. So that's the very basic feature of CDMA. Let's write that first. So this is actually a hybrid combination. Hybrid combination of FDMA and TDM. Okay, now let's try to be more specific over here, right? I know that in FDMA, user gets a specific frequency, right, for communication. So you want to avoid that, right? User should not use the same frequency all the time. This is the idea, because if you use same frequency, it means it is FDMA, and we know that, okay, somebody knows that you are going to communicate in the same frequency, then that's a problem for you, right? So our idea now in CDMA is that you have to change your frequencies, right, with time. So all the time you don't use the same frequency, right? But there will be frequency bands, right? Which means you have to jump from one frequency band to the other frequency band, right, at regular intervals of time, right? Again, the jump should not be something which is known to you, correct? In the sense, it should not be you should not be able to determine which particular frequency you are going to use through some equation. If it is an equational way, like 4t, right, every t you put 4t, go to fourth, like 4t means it's, yes, so there has to be a something like a random jump. You should be able to do a jump randomly, but among the available frequency bands. This is the first requirement of this, right? Because we are trying to make some hybrid combination over here. So let's look at the requirements. First requirement is that we consider FDMA as our basic system, and I want, in the FDMA, I don't want to fix the communication channel for the user. The sub-bands you should be able to switch at a random fashion. Now you go to first, then you go to third, then you come to second, once again go to third, be there in third for one more extra time, then come back to the first, then keep repeating the second band for 2 times, then like that. You see, it's a random thing, right? So like that, you should be able to do that. This is the first thing. And let's look at the modifications we require in time domain. Right, when it comes to the time division, so previously, what time division and who is sending, right, was predetermined, right? So first one allocated for first user, second for second, third for third, and this was repeating, correct? Now you will make sure that everybody will communicate in the same given time, right? Everybody will communicate. You don't restrict that, okay, only one person will do, right? That's what you want to bring the variety now, right? Right. So at different frequencies, right? But when the time frame changes, everybody will change their frequencies. Everybody will use the communication channel, but the sub band that you are using will be swapped, right? As you move from time frame 1 to time frame 2, whoever was using time frame 1, the sub band 1 will move to subband 2, 2 will go to maybe 1, and 3 will be shuffled with 4, and so on. Okay, so like that. So this is our requirement as of now. So let's try to write the requirement first. Okay, so that is, I'll just write the requirement. So FDMA, in terms of FDMA, right, the users must change their frequencies at random, right? It should not be fixed. So earlier it was fixed. In FDMA we want this change. Okay. In terms of TDMA, the modification we are expecting is that, right, instead of one user communicating in a given time frame, right, all the users must communicate. Okay, so these are the basic requirements. Let's modify this if required at a later stage. So let us try to look at the diagram. Alright, so what will happen to the time frequency diagram we considered earlier? So the vertical axis is frequency and the horizontal one is the time. Now we knew that we had divided either in this fashion or in this fashion, right? Previously. Now what we do, we club both of them, in the sense just now what I draw finally, right? I'm going to have rows as well as columns in this case, okay? But we will separate, we need the guard bands in between, correct? So because of that, let's try to draw something maybe like this. Alright, yeah, so I'll try to generate something like this, correct? So you see, I'll try to horizontally, if you consider, this is time slot 1, but I'm using all the 3 frequencies, okay? Now let's come to this. Then okay, now we can see the guard bands that exist between time frames as well as the frequency frames, correct? So you can see that okay, let's give the time frame here. So I can see that this is time slot number 1, this is time slot number 2, this is time slot number 3, and so on, right? At the same time, let's mark the sub bands over here. So this is sub band number 1, band number 2, and this is the band number 3. Okay, so this is band number 1, this is band number 2, and this is band number 3. Now you see how the users are using this. So I will allocate band number 3 for say I'll simply write U1 indicating user 1. This is for user 2, this is for user 3. It's at random, okay? I'm writing at random. You see, it's not in any order. Then let me say that user 1 shifts here, user 2 shifts here, then user 3 comes to this. Okay, later on maybe user 3 remains here, but user 1 and user 2 swap. Possible. Right, so you see that we try to match our conditions that we try to write. Users must change their frequencies at random. This was the first point which we discussed. Correct? So now you can see that is happening over here, and you see users are switching. Correct? So users are switching their frequencies with the different time slots. And we can also see the second requirement. The requirement number 2 says that everybody should be able to communicate in a given time frame. So you can see for a time slot 1, all of them are communicating, right? Even time slot 2, everybody is communicating, and so on. Time slot 3, 4, any number of time slots you have, you still have the communication that is happening between all the users of the system, right? We can also note that there is a guard band, alright, guard bands, one over here and one over here, okay, in terms of the frequencies, right? In terms of the guard slots or the buffers, we can find them over here. Okay, so that's how the hybrid system has been brought into picture by converting or by combining the FDMA as well as TDMA, and we call it as a CDMA system. Now we'll come to the technical aspects of this, right? What are the exact requirements, and what do you call this, the terminologies? Okay, so the first term that we are going to use here is called as the frequency. See, the users change their frequencies at random, correct? So they jump from one frequency to another frequency as the time slot changes, right? So this aspect of the CDMA is called as frequency hopping, HOPPING. Right, this has to be employed just to ensure that during each of the successive time slot, frequency bands assigned to the users are recorded in an essentially random manner. This is what is the requirement, and such a jump is technically called as frequency hopping. Okay, so frequency hopping means, let's try to write it in a sentence over here. This is required just to ensure that during each successive time slot, the frequency bands assigned to the users are recorded and reordered. You will register that, you will record that, okay, right now you are in this particular band. Next you will reorder that, right? So that's why you will record and reorder. Yeah, so we can say that in a random fashion. This is what is called as a frequency hopping. So example, you can say that in the time slot 1, user 1 occupies a specific, let's go back to the diagram and see. So user 1 is in third band, user 2 is in the first band, user 3 is in the third. Next one, you will make a change. Time slot 2 means user 1 hops to a different band, user 2 will also hop, and so on. Right? So such an arrangement has the appearance of something like you are actually changing your position, right, continuously, right? You change, time slot changes means you change your frequency band at random, correct? So you try to bring into the bring the concept of security in place, right? So compared to the TDMA and FDMA, right, this particular hopping provides secure communication. Okay, now how this is achieved? That actually is a completely different concept under our communication, and this kind of jumping, you see that it is actually a modulo operator, right? In the sense I can go from 1 to 3, then I don't have to go to 4 because fourth band does not exist. After that you have to come back to 1, 2, 3 once again, but not in the same order. You jump at random, but this is a modulo operator, correct? So this kind of jumps are actually controlled by a cyclic codes, correct? So if you remember cyclic codes, somewhere you might have studied codes called as, right. So it's actually a part of digital only, right? It might come in the digital, or even you might have studied information theory or any subject related to this, right? So coding will come over here. Cyclic codes, specifically called as PN sequences, right, are used to determine the random frequency hopping, right? So here the PN basically is a short form for pseudo noise, right? So it looks like a noise for you, right? It's a completely random generation of numbers, but it's actually not noise. It's a pseudo noise. It looks like noise, but you intentionally create that. There is a formula, but the formula is not easily available. In the sense, you cannot determine the formula by just looking at the sequence, right? Only if you know a logic you can generate the sequence, but reverse engineering is not possible. Okay, so such sequences called as PN sequences. It's actually a specific type of code. We use these kind of pseudo codes in encryption, right? So random generated numbers, right? So you can use a modulo operator definitely over there to restrict your number generation to some limits, like 1 to 4. Right, I have only 4 bands. In the sense, you have to jump only, you have to generate a number between 1 to 4. Okay, so make it modulo 5. Always the number generated will be modulo 5, like 1, 5, 4. Oh, sorry, 5 is not there if modulo 5 is used. 1, 4, 3, 2, 2, 3, 3, and it's a random fashion. Okay, so at what particular interval of time, what particular frequency you are going to use will be determined in terms of the band number. Okay, there is another completely wide topic in communication to discuss about the usage of this. It's called as a spread spectrum communication. All right. So there you have variety of spread spectrum communication, which actually is more secured way of communication, right? It actually deals with the two things. One, if you are going to communicate, right, in a very secured fashion, how do you make sure that your communication is not being detected by anybody else? You are communicating, right? But anybody else, let's say you have a radio transmitter, and you have designed a radio receiver, and you want to give it to your friend. Only you two can talk. You two can use. I know that, okay, your frequency is 100 megahertz. Definitely, I know that. But you, in spite of knowing that you are communicating at 100 megahertz, I should not be able to listen to you. This is the idea, right? This is, you are communicating, but you want to make it more secure, right? Undetectable by anybody else. This is one aspect of spread spectrum communication technique. Okay, coming to the second aspect of the spread spectrum communication is that, right? It's like somebody is communicating, like the same example. You have a radio transmitter receiver. You and your friends are doing a communication. Now, I know that you are communicating. The first aspect was you are making sure that I will not be able to listen to you. The second aspect is that I will jam you, right? I know that I will identify what frequency you are communicating, and I will jam. That's the other aspect, right? Both are coming under somewhat advanced topic of communication, specifically digital communication, and it is called as spread spectrum communication. Okay, so the basic idea is that when you are communicating with your friend, you try to keep the energy as minimum as possible, power as minimum as possible, so that somebody who is listening to you, they assume that this is a noise, right? Very basic idea, but there are some codings coming up. You try to use some codes and try to change your frequencies, etc. Right? And the other case is that we introduce noise in such a way that the other person receives only noise. So your communication will be jammed. Okay, so these are the two aspects of this. So out of that spread spectrum communication, one small part is CDMA. CDMA is a very little part of that. Okay, it actually overlaps with spread spectrum communication and the multiple axis techniques. So to derive this CDMA, you are using the other two multiple axis techniques. All right, then we have another specific multiple axis technique. This is called as the space division multiple axis. Okay, this is SDMA. Right. Now, this is somewhat slightly different technique. On a small scale, this SDMA is not useful, right? It is specifically applicable whenever you are going to divide the customers or divide the users based on their location, geolocation. For example, once again, we can go back to the mobile communication technique or specifically the satellite communication technique. Like, for example, so maybe there is a service provider for the channels. Okay, now you see region based channels are, right, required for a only specific region. Like Karnataka expects more Kannada channels than maybe Oriya channels or Northeast languages, correct? So you see region based division will happen, right? So this region, whoever is present in this region, you give an access to them to a specific channel based on your location. So space division, you divide the entire space into several sub regions, right? It is location based, right? So you identify the location of the user and provide the access, right, according to what region the user belongs to. right? So in this particular technique, so the resource allocation is achieved by exploiting the spatial separation on, I would simply write Earth, right? The other example could be like whenever we opt the uh, maybe we'll go to the telecommunication field. Like I want to seek help from some customer support, right? Maybe depending upon from where I call, I get the language options, right? Depends on that. So I for me there is no meaning in getting a language support in French, German or something, right? Maybe two or three languages of my country will help, like that. So depends on the service provider will have all the languages, but you will get an access to only those languages which are relevant to you, right? So this is one example of that. So when it comes to the how this is built, right? There will be a sensor that is based on sensing the location of a user, right? It has to be identified. If you are using internet for this purpose, it is very simple. Simply the provider will look at your IP address. That gives you a very clear cut idea saying that okay, this is the location. Fine, that is one thing. But when it comes to the, say, a difficult one such as yeah, satellite. Let's go back to the satellite, which is a very good example. They will use multi-beam antennas. Okay, so the beams are located, the beams are directed towards different regions on Earth. So, using which beam the user is communicating with the satellite, it will identify what are the access to be provided to the user. In the sense, there is what is called as a beam forming, right? So, you can actually concentrate your signal to specific direction. We call it as a beam, right? Antenna and wave propagation. We have used the word beams several times over there, correct? So, in that case, you see there is what is called as multiple beams, right? Using those multiple beams techniques, you can identify which direction the user is located and what are the services that needs to be provided. So this is referred to as on board switching. So it refers to select proper antenna beam for transmission. In the sense, the restriction that we wanted to bring into place by looking at the location of the user, right? So that is possible by using this kind of switching, right? So, in other words, in case of this, what you call satellite communication, uh, different Earth stations are enabled to access the satellite transponder simultaneously on the same frequency slot or a same time slot, right? But the contents are different. right? You can allocate different contents to different stations, right? Like this. So time slot is same. Let's say this is the satellite which we are talking about, okay, and it has say two beams, right? Yeah, there is a station, base station over here, right? There is another base station over here, let's assume. Okay, now the basic idea is that you can, the simultaneous communications will happen between this and this, right? Like at a given frequency f1 and at the same frequency f1, right? But you see, depending upon their geolocations, right, the contents or the message will be different. Okay, the first one will receive a message M1, the second station will receive a different message M2 at the same frequency, because right, you see the beams are different, they are getting different depending upon the geosocial locations, right? The contents are different. This is location 1 and let's say this is a different location number 2. So that's what is called as the space division multiple access. Okay, now overall idea, let's look at the overall idea of what you call as the multiple access technique. Right, one thing that is very common among any of the multiple access techniques that we use here is that they are trying to allocate the communication resource such as a satellite through the usage of some disjointedness. Okay, this disjointedness is also sometimes referred as orthogonality. Okay, maybe it is, what are the parameters of orthogonality? One is time, right? You can make use of time as a disjoint slots. Nothing overlaps. First thing. Second thing is the frequency. Right? You may have different frequencies allocated and you will make sure that the frequencies do not overlap, or in simple words, you try to make the frequencies as integer multiples of each other. So when the frequencies are multiples of each other, when the frequency bands, the central frequencies of each bands are integer multiples of each other, you say that they are harmonics. Correct? And when we are using the harmonics over there, right, we know that they are, most of the time they are orthogonal to each other, provided you use a sinusoidal carrier, like sine wave or cosine wave, etc. you use as carrier, means they are orthogonal to each other. So that is the second aspect, that second feature which you can try to, second parameter which you can use to share the resource. The third one is the space, right? So using all of them, right, you try to make use of the particular resource for communication, right? And this kind of communication is commonly referred as what is called as a broadcasting, right? So normally we say broadcasting in terms of refers to the TV and the radio channels, but this kind of, whenever you share a resource and communicate, that itself is a broadcasting. You see the TV channels, normally we say channel broadcasting, because the whole TV band, the visual band is divided into several channels and each channel uses that. That's why we call it as a broadcasting, but that is same broadcasting is the term used when even several users use the same frequency band or same time divided into time slots, or sharing the resource based on your location. Yeah, CSMA is actually, it's not a communication multiple access technique based on the communication aspect. It is actually, if you remember, we have studied this as a network protocol, right? So it's actually a protocol, like you send a protocol to different users, right? whenever you send that and you allocate a specific timing to that, okay, I'll quickly write about it. It's not actually a multiple access technique as we have seen, right? Okay, but I'll try to finish that quickly. Okay, just let me write. Okay, this is carrier sends access. Okay, now let us now let's try to assume that there are 4 different devices connected to a network. Okay, so let's say this is device A, we have a device B, and we have a device C, and so on, right? So all of them are connected, right, in some format using a network. It can be star connection, right, or any of the other standard way of communicating. Okay, so let us try to denote this is the time. Okay, as I move from top to bottom, there is an increase in time, right, in the sense when A sends a message, right, this is the point when A sends a message. Okay, and there will be a what you call as a deadline. This is the deadline. Within that time, my message from A has to reach its final destination, irrespective of where is that the destination. Okay, where the destination is located on the network, right? Each packet will take certain time to travel through the network, right? Maybe it's in the speed of light, possibly, right? But it takes some time, right? Fine. If within that time limit, maybe this duration, what you call, say, 2 seconds, within 2 seconds you want to reach, otherwise that is lost. So normally we call that term as what you call as a propagation time, or it's a delay time associated with that. Okay, so always we have that term coming into picture. So now I can call this is the P, the propagation delay, or the final time, the maximum time is allocated. Now you can see that it starts from A, it goes to B, right? Then it actually takes more and more time and it crosses this. The time taken to reach C is here. Right, now you see this is actually A actually sends a carrier. Carrier is the carrier of your message. By using certain techniques you can send, right? So we have variety of signals that maybe in the packet format. The most common format is a packet. So you convert your message into packet by doing encapsulation, right? If you remember the term, perform encapsulation and send it. Okay, so carrier will take, now the carrier is sensed over here by B, right? So carrier sense will happen at this point. At this point the carrier sense will happen, but this time is outside your maximum allocated time. So this packet is here, it is not valid, but at this point it is valid. So you see the multiple access of your message sent by A is possible, but in this case C is not valid. A has to send once again. But you see that carrier, once it gets sensed by the devices, they are able to access your message. Okay, so carrier sense, whenever the carrier gets sensed, you get an access. Alright, so this kind of technique, it's actually a network terminology. It's called as CSMA. Right, so again you have 2 varieties under this. The one is called as CA and one is called as CD, that is a I think collision detection. Okay, one is collision avoiding, CA, one more is that. Those are the two different techniques. We have to go a little bit in detail to understand those concepts, but just to define the CSMA, I think this explanation is sufficient.